now. Now look at this exponential equation. 4 to the power of 2x minus 10 times 4 to the power of x plus 16 equals 0. We have a question as complex as this one. The one we're looking at now, Jeremy, is that the one you're asking about? They're calling complex. This one here? No, the one before. It's not that complex. I don't see any reason why I couldn't put that on the test. Right? It does have a couple of steps in it, but I think that it's perfectly reasonable because we've done it for you to be able to get that answer. All right. Okay, let's get to this one now. This is another exponential function, but a lot different from the ones we've done so far. Any ideas as to how we might be able to tackle this question? Okay, I see a hand going up, and that hand goes to Jeremy. Jeremy, go please. So you're thinking maybe the 16 would be 4 to the power of 2, then is what you're saying. Yeah, but it's not like you're saying this is equal to this, though. If that's the case, then yes, you could do that. Let me show you another strategy that would be useful in this case. Let's do a substitution. Let's let, I don't know, y be equal to 4 to the power of x. Let's say that that was a substitution we wanted to make. Well, what would y squared be equal to in that case? It would be equal to 4 to the power of x to the power of 2, wouldn't it? Which would be the same thing as what? 4 to the power of 2x. Can we agree on that? 4 to the power of 2x. Okay. So now here's what I'm thinking. Why don't I rewrite this function in terms of y? You see this 4 to the 2x right here that I'm pointing to? Instead of it being 4 to the, let's write that as y squared. And it says minus 10 times 4 to the x. Well, why don't we say minus 10 times y? Because we said that y was 4 to the power of x right there. And then plus 16 equals 0. So now we have essentially a quadratic function. And I'm thinking I can do this because I've done quadratic functions a million times in grade 10. Well, maybe not a million, but a couple of times in grade 10. So I'm going to go ahead and factor this. This is all in terms of y so far. And I think you'd agree with me that I'd say that this would be y minus 2, y minus 8. I think you'd all agree with me on that. But I could factor it that way, equals 0. So that means that y has two values, 2 and 8. So is that my answer? Am I done? You guys are way ahead of me. No, we're not done. Why are we not done? Yeah. Now we need to let the y values be equal to our 4x. We have solved for y. Perfect. The question didn't ask us to solve for y, though. The question wanted us to solve for x. So now we have our values of y. What I'm going to do now is I'm going to let each of these be equal to what y was. Y is equal to 4 to the power of x. So it means that 4 to the power of x is equal to 2, and 4 to the power of x is equal to 8. That's what we're saying. That's what we're saying. We have our y's, but we need to find our x. Well, for us to do that, we're going to replace that y with what y was in the first place. Y was 4 to the power of x. So I'm taking away the y, and I'm putting 4 to the power of x and setting that equal to 2. So now we have solved this before. If 4 to the power of x is equal to 2, how do we solve for that x? All right, any thoughts on how we can solve for that x? If 4 to the power of x equals 2, let both have a base of 2. Okay, that's a good strategy. So I'm going to call this 2 to the power of 2 then, to the power of x. I'm just going to call this 2 to the power of essentially 1. Right? Now, the left-hand side of this, I can write as 2 to the power of 2x. Hopefully everybody agrees with me on that. The right-hand side of this is 2 to the power of 1. If I'm going too fast, please, please, please slow me down. Stop me. Tell me, Mr. Kamuk, you got to slow this down. All right? But I'm hoping you're okay with that so far. Now, here's where we get to the point that's similar to what we had before. Because now I can say, okay, that means that 2x is equal to 1. I don't need that base of 2 anymore. And therefore, x is equal to a half. Now, is that, you don't get extraneous roots when we're doing these kinds of questions. So this is exponential. You get extraneous roots with log equations, but not with an exponential equation. So it looks like we're good to go. But is there another answer? Let's see over here. If 4 to the x is equal to 8, what is x? Well, why don't we set them both to have a base of 2 again? So instead of it being 4, I'm going to say 2 to the power of 2 to the power of x. Instead of it being 8, I'm going to say, right, was ahead of us. I'm going to say that this is 2 to the power of 3. This, of course, is 2 to the power of 2x is equal to 2 to the power of 3. And let's exponents equal to each other. 2x is equal to 3. And therefore, x is equal to 3 over 2. There you go. It was ahead of us on that one. And these are your two answers for the original equation, right? The two values of x are a half and 3 over 2, right? And to make it easier for us, what we do is make a substitution, right? Made a substitution so that the function would look more quadratic. If we made it that y was 4 to the x, then y squared would become 4 to the 2x, and we could substitute out that 4 to the 2x, and we could substitute this 4 to the x as well. And there you go. Answers are, will this be on the test? I guess you'll find out in about 2 days. Today's Wednesday. You'll find out on Friday. Okay? Anything that we're doing could be on the test. This is why I'm doing it. Okay. So, let's move on. Unless anybody has any questions, this doesn't bode with what? Why are you saying that, Jeremy? All right. I know that it's the first time you're seeing a question like that, but then once you've done it, then you have the resource of the video after this to go through it again. It's in the textbook, by the way. I think the very same question is in the textbook. So you can also look at that, and I'm sure you'll be ready for all of this, right? You're here to learn, and I'm sure that the more you learn is the better you are at this. Isn't that the case? I've always panted for a test. I think I'll be fine. I'm sure you'll be fine. I am sure you'll be fine. Okay, so there you go, folks. This function is an exponential function because the variable is the exponent. But if you make it look more quadratic, it becomes more manageable. Okay, now I want you to consider the following. There's a substance, and I'm sure you've heard of this before in probably chemistry or maybe physics, I'm not sure which one, about substances that decay, radioactive substances that decay over time. So this thing called polonium-218 decays to lead-214 and does so exponentially. 4 minutes after a 100 milligram sample of polonium-218 is placed in the nuclear chamber, you only have 40.96 milligrams remaining. Write an exponential function or equation that models this behavior. Now, there are two ways that we can write this exponential function, right? In fact, part 3 of this question says rewrite the equation for part 1 with a base of 0.5. So we're going to write it first, not with a base of 0.5. We're going to write it using the exponential format. Excuse me, hold on one second, please. Using the exponential format, where y is equal to some initial value times some base raised to the power of x. We need to figure out what the a and the b are that would make this equation work. I put in 100 milligrams of this sample, and after 4 minutes, I only have 40.96 milligrams remaining. So, can you help me out here, please, folks? Where do I put these various numbers that they gave us in the question? 4 minutes, 100 milligrams drops to 40.96, right? Because I need to figure out what the A and the B are so I can generally have an equation that models behavior. You think the A is 100. Good call. That's your starting point. What else do we know? Anything else we know? Do we know the y? Do we know the b? Do we know the x? What else? The 40.96 is the y. I don't know. Is that true? What do other people think? Jeremy's got some suggestions there. You agree? And so do I. So 40.96 over here. Okay, what else do we have? Because there's one thing that we don't have, and we're going to see if we can figure it out. But what else do we have? Liz agrees and Noah agrees. Good. Right? How about that 4 minutes? Where do you think that might go? There's only two other things remain, the b and the x. Right? So there's one thing we don't know, and Noah thinks it's the x, and so does Jeremy, and they're both right. That is exactly the case. We don't know the b. We don't know the base. That's what we don't know. Right? We know that if you put this in for 4 minutes, the initial 100 becomes 40.96. We just don't know what base you're using to get to that. But can we solve this? Can we solve it? So the B is a half-life. No, it's not. It's not. We're going to work that out. We'll get to that eventually. Right? We'll get to that's part 2 of the question. We need to figure out what this B is first. Right? How are we going to do that? How are we going to figure out the base of the... Now, do I need logs for this? Is that what you're thinking? Jeremy, go ahead, please. Mm-hmm. 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 Okay, okay. Interesting. Any other thoughts on how we could possibly solve for b? Because that's the thing that we don't know. We don't know the base, right? We have the exponent, we have the initial value of 100, we have the final value of 40.96, but we don't know the b. So, at least give me the first step before we talk about ultimately where we need to go. What is the first step that we need to do, you think, to eventually get the value of the b? Anybody? I think I saw a hand going up. I think it might have been Jeremy. Both sides by, okay, both sides by 100 seems like a good idea. So 40.96 divided by 100 is equal to b to the power of 4. Okay, does that make sense to everybody? I want to make sure that we're all on the same. Let me do a quick check in of the room here. Okay, Axel says yes. Kayla says yes. And Joel says, okay, good, 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 good. Okay, good. That's good. And by the way, dividing by 100 is easy. So why don't I just put 0.0, oh, that's too many. That's too, hold on, that's not right. That's only 2 decimal places over, need dividing by 100. So 0.4096 equals b to the power of 4. Okay, okay. But I still don't know what b is. Now, Jeremy was suggesting logs. Is that how everybody else feels? That we need to take logs in this case? Is that what the deal is here? Harish and Riddhi, let's see. Yeah, Harish says yes. Jeremy says yes. Is that how everybody else feels though? That this is a log question. Sheobun says yes. Joel says yes. Mr. Kamak says no. Sorry. This is not a log question. When do we use logs again? Run when you use logs. When you're trying to solve for what? What is it that you need logs? When you're trying to solve for the exponent, we have the exponent. We actually have the exponent already. So we don't need logs for this. Logs are not going to help us out in this case. Could we just like root or something? You know what? Now you're talking. Let me try to put it to you this way. Let me try to put it to you this way. You're on the right track now, and you all know it somewhere deep inside of you. You know what to do. But I'm going to give it to you this way. I want to solve for b. I want that b to be on its own. What if I took that b to the power of 4 and raised it to another exponent that would eventually make that become b to the power of 1? What exponent do you think I could put there? What other number could I raise it to that would be essentially, when I multiply those two things together, I would essentially get 1, b to the power of 1, which would be great because b to the power of 1 is b. So what do you think, folks? Minus 4? But if I put minus 4 here, it's going to be b to the power of minus 16. That's not going to work. But Jeremy is saying 1 over 4, and we can use a 4 to... That's exactly what we're going to do. But I'm just going to write that as... I'm going to write that as b to the 4 to the power of 1 over 4. But if I do that to the right side, I have to do that to the left side as well. 0.4096 raised to the power of 1 over 4. Now, the right side is going to become 1, right? Because 4 times 1 over 4 is in fact 1. The left side can be expressed this way as the fourth root of 0.4096. I made this point to you earlier on when we were looking at exponents, right? I said to you that a 1 over 4 exponent means the same thing as the fourth root, and that's really what we're doing. Yes. So really, oh, the 4 times, yeah, why is it 1? Okay. Because, Kayla, and I'm glad you asked, because multiplying 4 by 1 over 4 gives me 1. And if I take a power and raise it to another exponent, I just multiply those two exponents, right? Does that make sense, Kayla? It's called the power law of exponents. Do you see what I'm saying there, Kayla? Can you explain that again? I sure can. I sure can. And I'm glad you're doing that. I'm glad you're saying, that still isn't, I still don't quite get that. So one of the things you learned earlier on is that if I have, let's say, for instance, a to the power of b, then I raise that to the power of c. And that's the same thing as a to the power of b times c. Does that look familiar, Kayla? You remember that from before? Yes? Okay. So if I were to take the right-hand side of this function, which is already to the power of 4, and raise that to the power of 1 over 4, then that would be the same thing as taking 4 times 1 over 4 to get my new exponent, or 1/4 of 4 then. Isn't 1/4 of 4 1, Kayla? When I multiply 1/4 times 4, is not just 1? Would you agree with me on that? And that's why the eventual result of that is that I'm going to have b to the power of 1, which is exactly what I want, right? And then on the left-hand side, I'm going to do exactly the same thing. I'm going to take the fourth root of 0.4096. Okay? Now, the fourth root, if your calculator doesn't have that feature, is the same thing as this. The 4096 to the power of 1 over 4. So on your calculator right now, could you take the 0.4096 and raise that to the power of 1 over 4, which is the way of just how you find the fourth root. That's exactly how you find the fourth root, right? And I need you to do that on your calculator. You're welcome, by the way, Kayla. I need you to do that on your calculators right now and tell me what you're getting. Let me erase this in the meantime. What are you getting when you find the fourth root of 0.4096? Over to you, folks. What's your answer? What is the B1 equal to? Oh, sorry. Okay, so I'm getting 0.8 from Harish and Rachel. Thank you both. So I'm ready to write my function now. This is the missing piece of the puzzle. Here's my function, that my y is equal to 100 times 0.8 to the power of x. So you could figure out how much you had of this substance at any point in time by taking that 100 and multiplying it by 0.8 to the power of x. That's what we're saying. Thank you, Ava. Thank you, Rachel, and thank you, Harish. Right? And in fact, if I try that out with 4, I would get that 40.96 that we talked about before. Would it only be plus, you're asking? Okay, let me just see if I understand what you mean by positive. Would it only be oh, I see. Oh, I got you. I got you. Okay, when you're taking a 4 through, it could be positive and negative. In this case, the negative root wouldn't apply because we're talking because of what we're talking about here, right? We want this base to be a positive base, so that's why I'm going to say positive 0.8 here. But I understand why you're asking that question. Now, let me just say, Jeremy, let me just say one more thing I take your question. I'm going to put another page here for this. You're all of you already knew this before that if I was doing Pythagoras' theorem, for instance, right? I short put Pythag for short. That if you ended up with x squared is equal to, let's say, 36, that what you would do is you would find the square root of the two sides. Well, what you were in effect doing is this: raising x to the half, x to the 2 to the half, and raising 36 also to the half. The x squared to the half gives you x to the power of 1. You really didn't realize you're doing that. And of course, the raising 36 to the half means the same thing as finding the square root of 36, which of course is equal to 6. So you've been doing this all along. You've been taking the inverse or the reciprocal of the exponent and multiplying it to get it equal to 1, but you have to do it to both sides. And that's why when x squared is equal to 36, then x is equal to 6. It is plus and minus 6, you're right. I think somebody was asking that earlier on. In the case of the one that we're doing now, it would only be the positive root, not the negative root. That would apply. Okay, so let's go back. Let's go back. So we've answered part 1. All we've answered so far is part 1. That's it. That's all. Now, determine the half-life of polonium. In other words, how long is it taking for the substance got to more than half, right? It got down to 40.96, which is less than half. Half of 100 is not 40.96, so it's gone way past that. So how could we, with this base that we just got, right, a base of 0.8, how could we now come up with the half-life of polonium? That's the question we're trying to figure out here, right? Okay, Jeremy, hold your fire for a minute. Hold your fire for a minute. I want everybody to think about this. We've done questions like this before when we were talking about doubling time or doubling money, I should have said, right? How long does it take for you to double your money? Now we're asking how long is it going to take you to half where you started off? But the fire's burning. Okay, just quench that for a little bit. Okay, I'm going to get to it in a second. I don't want to have to call the fire department here. Um, so I want you all to think about that. So Jeremy, tell me now, how do you think we can come up with the half-life of polonium? What are you thinking? Mhm, mhm, mhm. Okay, good, good. Yeah. So now we're going to say this is part 2 of the question. By the way, we've done part 1, right? This answer here is our answer for part 1. Part 2 is asking, well, what's the half-life of polonium? How long does it take to get to half of where it started off from? And what Jeremy says is right. We're going to put 50 as our final value. 100 is still our initial value. And now we know that the base is 0.8, but we don't know how many minutes that takes. This is in terms of minutes. So now we're going to try to solve for that. And I think we all know the first step is to divide both sides by 100. So I think we all know that. So it's going to be 50 over 100, which is a half, is equal to 0.8 to the power of x. Okay. So this is a half, 0.5 is equal to 0.8 to the power of x. How do we solve for x this time? Can we do now is when we bring out the log machine. Okay? This is the time you gotta bring out the log machine. Because before you weren't solving for an exponent, now you are. Now you are. So how does this work again? Well, in the interest of time, I'm going to show you how this works. I'm going to take the log of the right-hand side, the left-hand side, 0.5, is equal to the log of the left-hand side, 0.8 to the power of x. Then I'm going to bring that x in the front as a coefficient. So x log 0.8 is equal to log of 0.5. Then I'm going to divide both sides by the log of 8. So x is equal to the log of 0.5 divided by the log of 0.8. Okay? All right, I'm going to have to depend on one of you now with your trusted calculator to come up with that answer. And that answer needs units. And I need to tell you what those units are. So please, folks, grab your calculators and tell me what. And of course, it's going to be an approximate answer. Quick question. Could you use the log base? Yes, the log base 8 of 0.5 would be the exact same thing as this. Yes, absolutely. Right? Using the change of base, it would absolutely be that. Okay? So give me approximately what that's equal to now, please. Anybody on your calculators. The log of 5, 3.11 I'm hearing. Okay, I'll use a 3.106. What units make sense for this? Let me take you back to the question for a minute. Let's read that question again to yourself. And you tell me what, because I'm going to put a statement there, but I need some kind of units for this. And I'm hearing minutes. Not milligrams. No, it's minutes. Because I was asking for the half-life. So it's time. So therefore, I'm looking for some measurement of time. So it's not milligrams. All right. So here's my answer then. The half-life is 3.106 minutes. Short for minutes. Okay, so we've done part 2 of the question now. Let's get to part 3. Part 3. We haven't tackled part 3 yet. Let's go back up and look at part 3. All the way back up. Rewrite the equation in part 1 with a base of 0.5. The base that we were using was 0.8. Now we're saying we want to rewrite it with a base of 0.5. Can that be done? It sure can be done. And I'm going to show you how that works. So, the 0.5 is kind of what you'd use for half-life equation. So here's what my equation is going to look like. So y is equal to 100, 0.5. But what am I going to raise that to now? That has to have something to do with the fact that it takes 3.106 minutes to drop to a half. So here's how it's going to look. It's going to be, unless anybody knows right away, I'll show you what that looks like. Anybody think they know what the exponent is going to be? It does involve that 3.106, which is the half-life. Right? How does that come into the exponent? Well, I'll show you. It's going to be x over 3.106. Whatever the half-life is going to be represented by that denominator. So the fact is that both of these equations, so either I'm going to circle them both. This equation, I don't know why I'm using yellow, right? And this equation are both equivalent equations. If I were to put them on a Desmos graph, isn't it 0.8? No, it's not 0.8 anymore because I'm now writing it with a base of 0.5. Oh, this is this is 0.8 here. But if I were to graph both of these, and you can try this on your own time, if you were to graph both of these equations, the same 100, same initial value, this is with the 0.8, straight to the power of x. But if I wanted to write as a half-life equation, then I'm going to put the 0.5 as the base to the power of x, the number of minutes, divided by whatever the half-life is. So every 3.106 minutes, this substance drops to a half of what it was before. So it is, in fact, Harish, 0.5 as a half-life equation. Put them together on a graph, they're going to look exactly the same. Well, not exactly, because we did round this to be 3.106. So the truth is that it might be a little bit different because this is a decimal, right? A rounded decimal. You're confused, Jeremy? Okay, no problem. Let's take you back then. Let me see if I can draw them both for you and then share that graph with you to show that they're both almost identical. They just have been written with different bases, right? You're saying that let's think about it this way before I go over to the graph. Every 3.106 minutes, 3.10, yeah, every 3.106 minutes, this is going to drop by a half. So let's just say, just for argument's sake, Jeremy, that this thing had been sitting there for twice 3.106. So let's say 6.212, whatever that is, 2.212. That means that this thing has dropped by half twice, because when I take the 6.212 and divide it by 3.106, I'm going to get 2. So I'm going to get 0.5 to the power of 2, which is therefore means I've dropped it by a half twice. And now I'm down to, I guess, 25 at that point, right? Because it would be 0.5 squared, which is 0.25. Is x equals minutes? Yes, x is in minutes. That's correct. X is in minutes. Yes, yes. Okay. And if you had time, and I don't think we have time today, but graph these two together. Go back to the video when I post it and graph both of these functions that are circled in yellow, and you see that they look very, very similar. Okay, so if I plug in for absolute, you could try that for yourself right now. So 100 times 0.5 to the power of 4 over 3.106 should give you something very close to the 40.96. It's not going to be exact because we rounded that 3.106, just so you know, but try it for yourself and let me know you got something very close. Okay, good. Let's move along. So we've taken an equation, right, and written it two different ways, one with a base of 0.8, and because we want it to look more like a half-life equation, we made it look like this. Now, we're going to generalize. Let me erase this. We can make any exponential equation that's increasing look like a doubling time equation. You might have heard people at one point when the pandemic first started talking about the doubling time for infections. How long is it taking for the number of infections to double? So they were using a doubling time model because it was going up. At some point, I'm hoping they're going to be using a half-life equation. How long is it taking for the number of infections to drop by a half? I'm hoping that we're going to get to that point someday. But the way things are going, I don't know. But anyway, so if it's an increasing exponential function, then you can make it into a doubling time format by taking the initial value, multiplying it by a base of 2, the doubling, to the power of x over d, where d is the doubling time. Or if as a half-life equation like what we just did, then the initial value times a base of 0.5 to the power of x over a half, where this h represents whatever the half-life is. In our case, we've got the half-life to be 3.10, whatever it was, 3.106, I think. So take a good look at that, because I'm going to see if we can take some graphs and come up with equations that are either doubling time format equations or half-life format equations. We're going to try to do that. And I've come up with some graphs that make it relatively easy to do that. Okay? So, by the way, Jeremy, are you okay now? You were not so sure before. Is it making more sense to you now? Are you good? Don't want to leave anybody behind here. Okay, good. So let's look at the first graph and see if we can come up with an equation for this graph. Now, let me walk you through the very first one. In fact, let me zoom out a bit here to give you a better idea of what this looks like. Okay, look at that graph. I want us to write an equation. Now, would this equation be a doubling time equation or a half-life equation? Which equation format do you think I should be putting in for this one? Doubling time. It's an increasing function. This hopefully is what the pandemic used to look like. Hope it doesn't look like this anymore, right? So this is where you have an increasing amount. As you go from left to right, the amount is actually going up in an exponential fashion. So I think the first part of this is, what's the I? That's the easy part, right? What's the initial value? Well, the initial value, of course, is what? Where's this graph? Starting from 4. Now, the question you're going to ask for the doubling time is, how far along the x-axis do I need to go before my initial value doubles? Let me say that again. The doubling time is based on how far I need to go along the x-axis, How long is it taking along the x-axis for my initial value to double? Okay, Jeremy's thinking 3. What are other people thinking? Right? I want to make sure I don't leave anybody behind here. Right? So I just need to be sure that everybody is okay. So it's at 3 is what Harish and Noah and Emily are saying. Is everybody else on board with that? It is 3, by the way, and really says 3. Right? And by the way, it just doesn't double from the 4. It actually follows that trend. And I'm going to show you what I mean by that. So initially starts off at 4, and at 8, you go across and down. It takes 3 to do that. Well, double 8 to 16. So it takes another 3 to do that. So now you're at 6. Right? If you were to double 6, you get to 32. It takes another 3 to do that. So now you're at 9. So every time you jump by 3, it doubles. So you started at 4, it doubled to 8, which took 3. It doubled to 16, which took you to 6. It doubled to 32, which takes you to another 3. So every 3 along this axis here, I'm doubling it on the y-axis. So I'm ready to write my equation now. Here comes my equation. My equation is going to say, let me go back to black actually, that y is equal to my initial value of 4 times my base of 2, because I'm using a doubling time format, to the power of x over 3. There's my equation, right? Because I'm using a doubling time, does it have to be a doubling time format? No, I could have used a base of 3, but no one's going to ask me how long is it taking to triple. I'd have to have a different exponent for that to work. But if I'm using a doubling time format, then this is what the equation would look like, right? And I can test this out with any value, right? I can put in, for instance, a value of 6. So that'd be 4 times 2 to the power of 6 over 3. I guarantee you I'd get the 16 from that, and so on and so forth. All right, we're going to come back to this equation shortly, but let's now take a look at this one, right? I want you to see if you can give me an equation for that function. I'm not going to say anything else. Don't put anything in the chat yet, but I want you all to think that through. Give me an equation for that function. Ask yourself a couple of things. What's my initial value? How long does it take to double? And what should that equation therefore look like? Right? I want a doubling. No, hold on. I was asking you to hold off, please. Just hang on. Don't want anybody put any answers in just yet. I'm not saying that no is either right or wrong. I'm not going to say that. Just want to know what other people think. All right? Think it through very carefully. Look at your initial value. How long does it take to double? And what should the equation be? All right, so you think you know. All right, that's good. Hold on to that for me, please, Jeremy. I want to give everybody a chance to think this through. Well, let's do this. Let's do this. Let's just do it one step at a time. Let me ask Liz. Liz, what would you say is the initial value on this one? So Liz, check in for me, please, and tell what you think the initial value is on this one. Liz, first of all, check in. Let me just hear from you first. Liz, are you there? Perfect. Give me the initial value, please, on this function. The starting point. Good. Now, see how long it's taking for you to double that. So move along the y-axis first and then read across on the x-axis and see how long is it taking to double that starting amount. How long is that taking? 2? No. Let me show you. You already said that this is my starting point, and I agree with you, right? We know that for you to double that, you're going to get up to 6, correct? Am I good so far, Liz? To get to 6. Good. So let's go across and see how long it took for me to get to that 6 on the x-axis and read down. You see what we're saying now? It's 5, absolutely. So Noah had an equation earlier on. Could you look back in the chat and tell me whether you agree with this equation now, or do we need to make an adjustment? I'm not saying it's either right or wrong. I'm just asking whether you think, just scroll back up through the chat and have a look at it. And tell me whether you think that is the equation that would work for this function. Back over to you, Liz. Let me hear what you think. I'm not going to tell you whether his equation is right or not. You think it works? Well, I'm going to write his equation down, and then we're going to talk about it. So y equals 3, 2 x over 5. Makes perfect sense to me. The base of 2 means you're looking at a doubling time format from 3 to 6. And guess what? This pattern continues. It doesn't just stop at 6, right? If I were to go up and see, how long is it going to take to go to 12? Well, that's the double of 6. If I read across and down, that takes another 5. So it was 5 to get to the first one, another 5 to get to the next time it doubles, which is, of course, at 12, because double 6 is 12. It does work. And you can try any number you like and put it into the equation. We're going to come back to these equations in a minute, because I'm going to be asking you what is the x value when y is 7. And we're going to look at the graph and see if the graph gives us a hint, and then we're going to do it algebraically. Okay? All right. Next graph. Here we go. All right. Obviously, something changed. There's a little different shape to this graph. It's still an exponential function, but it looks a little different, the ones that we did before. And let's see if maybe Harish can tell me about initial value and then where we go from there. So Harish, over to you. What's the initial value? Harish, first of all, check in for me. Initial value is 32. Agreed. So at least we know that the first part of the equation is y is equal to 32. What base do you think we're going to use this time, Harish? What are you thinking in terms of the base this time? 0.5. Because we're using the half-life model this time. Can we take it back up and have a look at that? So if you know how to come up with because it's obviously a half-life, what would you say the half-life is of this equation, Harish? What's the half-life of this equation? If you need me to make it bigger, just say the word and I can do that. It is in fact 6. So that would mean that this function is now going to have an exponent. Let me just bring everything down here. This function is going to have an exponent. Sorry, hold on. Go away, folks. Okay, there we go. Of x over 6. Okay, that's your exponent, x over 6. Am I leaving anybody behind here? I'm always sensitive to that fact. If there's something I've done that doesn't make sense, please give me, how did you get 6? Okay, Rachel, that's a good question. All right, let's see if we can figure that out now. Would you agree that 32 is the starting point, the initial value, Rachel? Okay, so let's circle that. And what's half of that? And by the way, you agree that this is a declining function. The function is going down, like how we'd like the coronavirus cases to go down. That's what's going on here. 16, okay. Just go down to 16. Let's read across to see how far we had to go to drop from 32 down to 16. Let's go down and have a look. Do you see that, Rachel? Right? It's always how far along the x-axis you have to go to either double in the case of doubling time or half in the case of half-life. Okay, thanks for asking. Thanks for the question. I appreciate that. And there's your equation. Right? There's your equation. Okay, there's one more graph. And I'm going to see if I can turn everything over to one person and say, hey, this is yours. Let me go grab my little wheel here and open it up. MHF, that's you guys. And whoever I ask, I want that person to give me the whole equation from start to finish. And that honor goes to Joel. Joel, first of all, check in for me, please. Let me know you're there, Joel. Where Joel at? Joel, where are you? There you are. Okay, good. All right, so here comes your graph. And I'm just going to turn things over to you and ask you to give me the whole equation of this graph. As I said, we're going to go back in a few minutes and do something more with the equations. But there's your equation. Can you give me, sorry, there's your graph. Sorry. There's your graph. Can I ask you to analyze that and give me the equation of that graph, please? The whole equation, everything. Just Joel right now. So 24, 0.5, so write that down. So y equals 24, 0.5 to the power of x over 4, he says. That's an exponent, and it doesn't look like it. So let me try to make it look more like an exponent. Give me 1 second here. Bring that down. And then just kind of erase that a little bit. Didn't mean to erase the whole thing. Well, let's see if that makes sense. Is a half-life of 4 reasonable? Starts off at 24. That's his initial value. Let's go down to 12. Let's read across and down. It does in fact look like 4. Okay, so let me challenge you now. We go back, and that's the last graph. Let me take you back now to the very first graph we came up with, which is this one here. What if I said, okay, let's see if this kind of works. I want to know what is the x value. By the way, Joel, well done. That was good. You got the answer right. What is the x value? And I'm going to erase all this other stuff here for now. What is the x value when y is 7? Now, we can go to the graph and ask the graph to give us a rough idea of what that answer is, right? 7 should be somewhere around here. So if I read across and down, I'm thinking the answer should be somewhere between 2 and 3, right? That's just eyeballing it, looking at the graph and saying, yeah, that looks like about right. But we have an equation here. We should be able to do better than that with this equation. So how can I figure out what the more accurate value is of x when the y is 7? Can I ask one of you to help me out with that? I want to know the x value that gives me a y value of 7. And I have an equation, so can that equation help us to do that? Jeremy, go ahead, please. Okay, so okay, hold on, let me do that. So 7 is equal to 4, 2 to the power of x over 3. Oh, whoa, what just happened there? X over 3. Okay, hold on, Jeremy. I think everybody's going to agree with you on that. I know you have something else you wanted to say, but can everybody buy into what Jeremy just said? Does that make sense? I'm trying to solve for x here, though. Okay, Jeremy, you wanted to say something else. Yeah, what's the next step? Yes. Okay, so let's go ahead and do that. So 7 over 4 is equal to 2 to the power of x over 3. All right, thank you, Jeremy. Somebody else can pick that up and tell us what comes next. I'm trying to solve for x here. What would you say? Log. Oh, I like that. Let's take the log of the two sides. The log of 7 over 4 is equal to the log of 2 to the power of x over 3. Okay, that's a good step. What would my next step be after taking the log of the two sides? Okay, hold off, Jeremy. Hold off. Let me see if somebody else has a thought on that. What's my next step after that? I'm trying to solve for x here, folks. Okay, Noah says move the exponent to the front. Okay, we can do that. So x over 3 log 2 is equal to the log of 7 over 4. Okay, Noah, Jeremy, hold your fire. What comes next? Can anybody tell me what my next step is? All right, so Noah and Jeremy have given you all a great start, but I'm still not sure what x is. Okay, I'm still not sure what x is. We took the log of the two sides, put the exponent in the front, but what happens next? Go on, I need some more involvement than just Noah and Jeremy, and there's been some other people. Let me just be quite frank about that. It's not just those two. The other people have stepped up as well. Harish, Joel, and some other people have stepped up as well. Right? But I'd like to hear some other AXA certainly has been there. You know, we've heard from other people, but I want a little bit more involvement here. Cancel the logs. No, we can't cancel the logs, Joel. We can't cancel the logs. If it was log of this equals log of that, then yes, we could do that, but we can't just cancel the logs. Where he says, bring the x over 3 to the left and divide the two logs. Okay, I can leave that x over 3 where it is for now, right? But you're right. We can say the log of 7 over 4. I'll leave it as that for now. I know it's some decimal. Over the log of 2 is equal to x over 3. Okay, Harish, hold your fire now for a bit. How do I finally get the x? I still haven't got x on its own. So there's something else that's missing here, right? There's some other step that we haven't done yet. And what's that next step? And then we'll go to the calculator. Right? How do I solve finally for x now? X equals what? It's x over 3 that's equal to log of 7 over 4 over the log of 2. So what's that next step that gets that x on its own? What can I do to both sides? Here's my clue. What can I do to both sides to make that magic happen? I need to solve for x here, folks. I need to solve for x. Anybody? Come on, folks. You can do this. Not Jeremy. Can't have Jeremy multiply both sides by 3. I like that. Multiply both sides by 3. So multiplying both sides by 3. 3 here and 3 here. This side becomes just simply x, and this side becomes 3 log of 7 over 4 divided by the log of 2. Now, the good thing is that you could also think of this, and some of you probably picked this up already, and you can say that this is the same thing as 3 log base 2 of 7 over 4. It would be the same thing, is equal to x. So either you do the one above it, which is the change of base formula, or you can do this one, or some people might even say this. It's the log base 2 of 7 over 4 cubed. That would also be another way to write that. At any rate, I'm going to grab my little wheel here. That was Joe the last time. I'm going to ask one of you to not, please don't put any answers in yet. I'm going to be asking one of you in a second to give me what that answer is. Interesting choice. So Jeremy. Jeremy, the wheel has spoken. What does that work out to be? And we know already, by the way, Jeremy, before you give us an answer, that the answer should be, according to the graph, somewhere between 2 and 3. If we don't get something between 2 and 3, then you know we messed up. Okay? So, over to you, Jeremy. Let me wait for your answer. Go ahead, please. Ooh, okay. Okay, go ahead. We're all going to sit on the edge of our seats collectively to get your answer. So whether you probably don't have a base 2 log thing on your calculator. So it's probably best if you use this there. 3 times, use a base 10 log key. 3 times a log of 7 over 4, use brackets around that, divided by the log of 2. That's probably the easiest way to do it there, Jeremy. All right, multiply the log base 2 by, let me see what Eva has saying here. Multiply log base 2 by t and 4 by t. Where is t coming from? Yeah, I'm not sure where t is coming from. Okay, Jeremy, go ahead. I'll check back with Ava on that. Yeah, go ahead. 2.422. Right. Mm-hmm. Mm-hmm. Okay, but that answer seems consistent with the graph, though. So what are other people getting? Now that we've done that. Ava, you had another idea there about how to do this. Did you get the 2.422 as well? You got the same, Rachel says, and Ava got the same thing as well. Okay. And again, that's consistent with what the graph is telling us. We should get something between 2 and 3. All right.